So first of all, just want a quick raise of hands. How many here have worked on a machine learning project? Okay, good number. And how many here would say they've actually they have a working machine learning system in production? Okay, handful. Okay, so definitely a discrepancy between those two. So last question: how many here knows about Lord of the Rings? Okay. Everyone's with me. So actually, I want to apologize. I think this meme is taken a bit over in this presentation, but I think this is the right crowd. Okay, so just a quick, a brief introduction to some of the projects that I've worked on. Started in working in astronomy and physics, and starting using machine learning to work on some of the problems that we had there to do research. One of the problems that we had was we had these telescopes looking at the sky every night, a big part of the sky, and you would basically get terabytes of data every night. And what you want to do is you want to see if something changed, because if something changed, it could be really interesting. So you couldn't really show all this data to hundreds of graduate students, right? You had to basically figure out some clever way of doing it, and there's some really heuristic algorithms that you could use. But we built this machine learning system that could really do this with extreme precision, and we ended up being able to detect things much earlier and much better than was possible previously. So another project that I think is interesting here is you can see the SO 2010 UI here, but we had this, with supernovas, as in the previous project, you had a light curve that was basically quickly up and then going down, right? And with a bunch of other kind of variable stars, you'd have a periodic light curve. And there's a lot of different versions of those, and they all correspond to some physical process in the stars. And you want to basically classify your catalog into each of these classes. And so we built a machine learning system to do that. But because there's so many classes, you'd have a lot of them that had very few examples, and you'd have to think about how would you actually go about and build a model that was good on all of the classes. So we started building algorithms that could ask the model, hey model, what should we actually try to investigate for you to become better? And so the model would return some places in kind of the space of variable stars that we should actually look at. And so whenever we saw any of those, we would present it in this interface to expert astronomers that were then going to help the model, and it improved much more rapidly than it could have done otherwise. So that's a process known as active learning, and it's starting to become interesting again now. What then happened was we decided to start a company. We've gotten some interest from industry, even though we were working in academia. And what does any group of nerds want to do? They want to build a system that can handle everything. And so we're going to build a machine learning as a service, and you could just put in your data and you get answers. And that turns out to be hard. I don't think anyone has solved this yet. I think some of the big players have some good services now, but in 2012, that was definitely too early. So what we ended up doing is trying to focus on something, and what we really wanted to show was, you could actually take these state-of-the-art machine learning systems and put them into a plug-and-play framework. Something that the user doesn't have to know that that they're actually working with the machine learning system. It just gives them value. And so what we started doing was integrating into these support systems. So basically, this is an example of of an interface where you get this support email, and we would say, look, here's the most likely answer to give the best answer to the customer. And if we could figure out how confident we were in this answer, we could actually start automating a lot of emails. And so that sounds a bit scary, to send emails automatically with actual, intelligent text in it. But it turned out to work pretty well, at least if you can control for your uncertainty. And one kind of funny story about this is, customers would be kind of confused when, an actual answer to their question would show up like a second later. And so we actually had to introduce this 5-10 minute delay so that it would seem more natural. And that just shows kind of the power of it. So last year, we were bought by General Electric. First, when I told people about this, they're like, what? Because that doesn't really rhyme with customer support. But turns out that they actually work a lot on many different things, machines that basically run our world. So you have everything from factories to trains and wind turbines and healthcare machines and factories and power plants, and all of those things is something that they work on. And it turns out all of those things generate a lot of data. And all of that data can be used to do a lot of interesting things, optimizing and making things safer. And our technologies fit very well into that area. So by now, everyone should be kind of ready for starting building their machine learning pipeline. And this is where the title of the talk comes in. There's a few things that we should think about before we do so. So first of all, it's really important to understand what you want to optimize for when you build your machine learning system, right? So one thing is the most traditional is accuracy. So this is an example of something that's not very accurate, but this could actually be or close to state-of-the-art object detection system a couple of years ago. Obviously, those systems, if you had like a super deep convolutional neural net, are extremely expensive to build, and probably more expensive to develop. And this is the answer you'd get, right? So it might be better than anything else you can get, but it also costs a lot more. So there may be some methods that you can use that are much better at this because you can constrain your problem space in some way, right? So in the same way as Michael talked about, right? Usually you deploy these things in a very narrow field. So you have some problem that you can actually define, and you have some knowledge about that problem that you can actually use to make the model much better. But nonetheless, in the world we live in, accuracy is kind of the most important parameter for a lot of people. So I don't know if you know Kaggle, which is a competition site for data science or machine learning, and everything that they do is based on accuracy. So you win if you have the most accurate model. Doesn't matter how many models are stacked together, or teams, or how crazy large it is, but you win if you have the most accurate model. And I think more than a few of the companies hosting competitions on Kaggle have actually found that the winning model is not necessarily the best one to deploy. And so another example of that, which is famous, is kind of the Netflix prize. So that was kind of what bootstrapped this whole machine learning competition field. And a good quote from Netflix was that they evaluated all the models, and especially the winners, which took a long time to find winners, because they were battling about the last 0.01 improvement to win the $1 million. And it turns out, they had to stack 10 different models to get to win. And it turns out that model was way too complex to actually put into production, and would take too much time for the engineering team to implement. So the lesson is, of course, you want to kind of think about how far do you want to go for the last percent, right? Because you may be able to get a really good model that is 1% less accurate, but cost 1% of the cost. So another great example of this is, or let's say, what I was talking about before was kind of the implementation cost, right? And so what I want to show here is kind of the runtime cost. So you probably all heard about AlphaGo from DeepMind and Google that beat the world's best Go player. And the point here is that it beat the world's best Go player, but it was using almost 2,000 CPUs and 300 GPUs real time to do that. And so I don't think that any of the companies that you work for would allow that in kind of a regular project with a normal ROI. So that was cool, but definitely not applicable when you actually want to run your model and make money. So obviously they've become a lot better and leaner and continue improving, but the point still holds. So another dimension that you should probably look at is interpretability. So from these kind of neural network deep learning areas, one of them is called convolutional deep neural nets. And what you'll see there is that if you work with images, there's actually some logic to how the layers are built. So if you were a computer vision person, 5 years ago, because probably there's not many left now, you would actually do exactly what this model has learned by itself in the layers. You'd start doing edge detection, you'd start doing texture detection, you start doing object and shape detection, and then you'd find objects, right? So this is what the neural net has kind of learned to do in its layers, and then you can start thinking about, previously what we did was we defined features and feature processes that would take raw data and transform it into something that the model could understand. And what you do in this case is basically you take your understanding of how you actually do computer vision, and then you build a network that can mimic that, right? So in the space of neural networks, I think we're moving from feature processing to kind of network architecting, and you have to start being clever about that, and especially in the name of interpretability and kind of transparency to how the results were made. So that one of the really tough parts of neural networks is that they're so complex you cannot figure out what's going on except in these special cases. And that's something that you would usually meet in your business, in your clients, in your organization, that they want to understand why did you actually make this prediction. And sometimes it's even regulated. You can't tell someone that they can't get a loan and not tell them why. So you can't use a nonlinear machine learning algorithm to do credit scoring, for example. So you have to do something that's more interpretable. So there's a lot of work to do here, and obviously something like Bayesian machine learning will actually improve this a lot. But there's methods and research in how you can do this on kind of more black box systems, and one of those is it's called LIME. So it stands for Local Interpretable Model Agnostic Explanations. It's basically just you run a bunch of permutations of data through your model to understand what comes out of it. And so it'll tell you which parameter actually meant the most in the answer. And I would argue that this is actually probably a good thing to do just in general as kind of a diagnostic step, right? Because you want to understand what is coming out of your model and why is it coming out before you actually start deploying it for real, so that you understand, what knobs can you actually tune to cheat the model, or if it's something that's actually sensitive, you especially want to understand this. Another kind of dimension to think about is, do you want to kind of automate, which is what I think most people think about when we talk about machine learning, or do you actually, can you actually do something that augments the user, right? So in the case of the self-driving cars, you have this 5 levels, right, which is basically from nothing to automatic. But you have all these levels in between that's kind of augmenting you in some way. And the same way with what I showed you in our support application, you could actually, we would just show the answer to the user, and they could click on it. But in the end, when we're confident enough, we could actually automate some of it. And that comes back to a lot of talk about, what's the risk of making a prediction and what's the risk of being wrong. And so you want to understand that to make the best decision here. So just a rundown of of what I just talked about, and you want to kind of try to get a holistic view of what your problem is and what you actually want to optimize for before you start. And so one kind of just advice and is to talk about the way that we kind of approach problems mostly. So the first is kind of, you want to go into a problem and really define the problem. And you want to understand what you actually expect to get for results, for answers. And so this is actually, a lot of people just start working on something because they have a hunch that something can be done. And there's plenty of fields where this is actually useful, and you can do unsupervised learning, you can do clustering, things like that. But if you actually want to solve, a real problem, and if you want to use supervised learning, you should actually think a lot about the results that you want to get. And so the second bullet point here is you need to collect, of course, but you need to understand the data really well before you start building any models. So I'll go through these points a bit more in the next slide. So let's just jump into that. So on the first one with identifying the problem, you want to understand, what is the cost. So this is kind of a you can set up a cost matrix basically of a wrong answer in various scenarios, or a right answer. What is the gain from that? And first, when you understand these things, you can actually define kind of an optimization metric that takes into account these specific values. So one example of that is the project with finding supernovas, is that we would be flooded with false positives. So basically, you'd get thousands of candidates every night that wasn't real. It was just some effect of the process or the image or noise or whatever have you in the real world. And so our optimization metric couldn't be just the best AUC under the best AUC, the best area on the curve. We would have to actually define an optimization metric that took into account getting a smaller amount of false positives. So our optimization metric that we use to build our model would be what is the accuracy at 1% false positive rate, right? Because then you're sure that you would have a manageable number of things to actually look through, and then whatever the accuracy was at that point would be what you could expect to optimize. And the next part about collecting and understanding data, I think there's a few pretty funny graphs here from Forbes that shows what does data scientists spend most of their time doing, and by far the largest part is cleaning and organizing data, and so that's great. And then the question is, what is the least enjoyable part of doing data science? And overwhelming number of people are saying cleaning and organizing data. So, it's just truth that in the real world, there will be a lot of messy data, and you have to have good practices and good methods for dealing with that. And a great example here is of understanding your data. So this was actually I think it was a recent paper where they were claiming they could detect gender from iris scans. And so if you're not looking at the data, could be the case. But if you looked at just a few of the examples, you'd have an idea of what was going on. So what do you think was going on? They're detecting mascara. So that's not a very good model, especially if you want to detect it from the iris. And there's a bunch of those examples. I think another one was during some conflict, they built a model to detect tanks in the landscape from satellites. And they got a really good model out of it, but when they needed to apply it, it didn't really work very well. And they went back and figured out that the model has actually learned to detect clouds. And for some reason, that just correlated with all of the tanks in the data set. So you want to understand the data before you start building your model. And then the next advice is to take the most simple, build the most simple model you can think of that solves the problem. So you don't have to look for fancy algorithms or understand TensorFlow to build machine learning models. There's plenty of old school models that work very well. And you should get it to work end to end. So basically, get it into the application, whatever you're trying to do, and get results out of it, get feedback, and from there you can start improving the model. And maybe you can show that it will actually be cost effective to start using TensorFlow or RNNs or whatever have you. But a lot of the times, you can actually get really good results from more simple things. And it's much more important to understand, the feedback and have that entire loop in place, because then you can move fast. So I guess that's just simple agile. But in the data science world, we don't always understand all the normal engineering practices. So I would say we're getting closer to being ready. One thing that we are missing, though, is to deploy this and to use these best practices. It's really important to have a good kind of infrastructure to do it on. And that doesn't mean it needs to be complicated. It just means, again, that we should learn from decades of experience in building software. And so one thing that we all know is this notion of continuous integration and this whole fancy loop of steps that you should go through and continue on. And I would say it's not really that complicated. We just need kind of one more step to look at some data in the machine learning version of this. Because you also want to do testing, you also want to do releases, you also want to operate it properly and measure it and so forth. So that's just something that I've seen a lot of data scientists, machine learning practitioners forget. That these things are not, these are still services. These are still things that you are actually building. And so when you build something and you get artifacts out of it, that sounds like a build system. So you can use Jenkins or whatever have you, right? That you probably already have installed. The other thing I would say is we've gotten a lot of really good things out of using containers. So I was happy to see a Docker container in the previous talk as well. And I'm going to go through these kind of 3 reasons that I think containers are really important for machine learning. So one is packaging. So I don't know if you've done this search, but I think a lot of people have and gotten results like this. So some NumPy version is not compatible with some TensorFlow or GPUs or whatever. Containers are really good at solving this problem, right? So you can install any number of packages, and you are sure that they won't conflict with whatever you have on your production servers or anywhere else for that matter. So the next one is inheritance. So you can actually use this, and I don't know how much you're familiar with Docker, but they have kind of simple inheritance based built into them. So basically, you can take a TensorFlow model, you can build your specific model on that, and then you say, okay, I want to actually specialize even more, and you can take your special model and build whatever special on top of that. So you can start having a kind of a tree of algorithms and models that you can use and deploy kind of in specific situations. And so that becomes really useful when, obviously, when you want to minimize the time it takes to build a model, you can actually apply these standard models. And then the last one is this notion of immutability. So really, a container makes kind of this complicated pipeline that supervised machine learning is look pretty simple, right? It's just something that where data comes in and answers come out. And so the most important part is really that you can use the same pipeline, or you have to use the same pipeline when you build your models and when you make predictions. And this sounds simple, right? But you see a lot of instances where you deploy the model separately. You have some code that actually is transforming the data, but those are separate repos or separate services in your system. Then you start updating the code because whatever you found bugs or you have new developments, but the model is still the same, making predictions. That means you can't trust the predictions coming out because you don't have the same kind of data coming in. And so you really want to make sure you use the same pipeline, and you want to put as much of the pipeline that you can into the container. And so this is really a good reason to have, in Docker images, where you get a kind of a unique ID for a specific container image, and whenever you change something in there, this ID will change. So it's a hash based on what the content is, right? And that means if you apply the same exact ID to the predictions as you did when you built your model, you know that the pipeline is equivalent. Okay, so the last point in kind of the infrastructure part is, you should use kind of great frameworks and services that already exist, right? So we already talked about Jenkins and kind of thinking the data science machine learning pipeline as an engineering process, right? But obviously, to actually build the models, just some of my favorites, if you want to get started, is scikit-learn is really good if you use Python. You can actually build these complete pipelines in scikit-learn and have optimizations done over the entire pipeline. And that's something that's really useful to do when you're getting started. Now that may not scale for exactly what you want to do, but you can also use something like TensorFlow, which is more of a steep learning curve. You have to understand what's going on. There's a lot of things to get right. But again, with Docker and containers, that becomes much easier. And TensorFlow has these really nice things with an actual kind of dashboard where you can go in and you can understand what's going on with the model kind of as it is building and afterwards. And the other thing that TensorFlow has is this layer that you can actually use to produce a prediction service from your model. And that becomes really useful when you want to run things in production. And then lastly, it was great seeing the Bayesian talk, but when I want to work in that kind of field, I usually use PyMC, and I find that really interesting to play around with. So I want to mention just a new project that I think is really interesting in this world of putting models into a production setting. And that's something from a new lab called RISE Lab. And if some of you know, the previous version of this was called the AMP Lab, which is basically the lab at Berkeley that built Spark and a bunch of other tools. So this iteration of the lab is called RISE Lab, and they have this new project called Clipper. And so this does a lot of what you want to actually do with your models. You want to be able to deploy them with kind of your framework of choice. You want to have it easy to update and add models, and you want to try to understand when you should upgrade, right? So it's not necessarily the best thing to just upgrade the model, not even if the accuracy is better on paper, because you don't know if the problem actually changed along the way. So you can actually you might want to deploy a model that has worse accuracy, but does better on new data because the problem changed. So one notion that they have here is trying to dynamically select the best model, and so that's an interesting approach where multiple models can be running at the same time, and you run your data through it, and you check the answers afterwards, and then you kind of select the model that works the best. So that's an interesting built-in part of this, and obviously a lot of kind of other interesting things in this project. So I think that'll be interesting to watch. And lastly, of course, some really interesting things can be done on the kind of public clouds, and the big players all have kind of machine learning platforms. And one obvious thing to do if you're working in TensorFlow is obviously to use the Google Cloud Platform, which is just kind of TensorFlow as a service. But the others actually have really good environments as well. That's worth checking out if you wanna work on that. So just to recap the infrastructure part here, you want to certainly use kind of best engineering practices, use continuous integration. Containers can actually be really important in this field, and then obviously wherever you can, you should use something that others are using. So I want to have time for questions as well. So I want to wrap up just by telling you a bit about kind of book I wrote last year. So this has a lot of kind of the advice about data and models that's not actually going into specific models. And then a couple of groups that I've been part of here. So one is the data science and machine learning group in Copenhagen, and if you're interested in kind of the nitty-gritty of practical aspects of building and deploying models, you should definitely check that out on Meetup. And there's this interesting organization called Nordic AI, where we're starting to do a lot of events and getting some really interesting folks to speak. And with that, I want to take questions.
So there's no questions from the app, but if anyone has one in the audience, please raise your hand. Don't be shy. Okay, there's one. Perfect.
Hi, thank you for the talk. Can you talk a bit about testing machine learning models and how you automate that?
Yeah, so it's obviously a bit different because you have this whole notion of data coming in, right? So you kind of want to do your testing on more levels than you do in normal software. So you probably want to do testing at the data level as well to kind of understand what's coming in, and then you want to do testing at the model level to understand, are the results that are coming out what I expected? And this goes back to kind of some of the first things that I said was, try to understand the problem and what you expect to get out of it, because you can actually think of, doing kind of test-driven development where you define that up front and you can write those tests and then you build your model to see what it's saying, right? Obviously, usually in these models, there's some randomness to it, so you can't just have, actual values, but you can have some range of numerical values, or you can have some general understanding that you can code in your tests. But then, of course, you usually are building this into kind of an application or a pipeline, and at that level, you can also test kind of the full end-to-end. So something comes in at the application level, API or UI or whatever it is, and you actually test the model by putting data kind of all the way through that pipeline.
Hello, thanks for the talk. My question is, once neural network is deployed to production, do you need to retrain it at one moment, and if yes, how often?
Okay, so that really depends on what you're modeling. So if your data changes a lot, you should understand the timeline that the data is changing on, and that should be, that should kind of tell you a bit about what the proper rate of rebuilding is. Now, obviously, that also becomes kind of a cost question, right? It can take a lot of compute power to rebuild the model. So you want to understand, how often do you want to do that compared to the savings that you get. So I think that's the best answer I can give.
Any more? Doesn't seem to be the case. Well, once again, very much thank you, Henrik. Thank you.
Yep.